Hey, good afternoon, everyone. Welcome to week 10, ITIS3P91. How is everybody? All right, are there any questions? Okay, today is our week 10, and we are going to do 3 items. Lesson 40, one sample chi-square test, sometimes also called goodness of fate. And then we'll do lesson 41, two-way contingency table. The third item is logistic regression. It is not available on the handout. That's why I provide this PowerPoint slide. You can get this PowerPoint slide on Sakai. Next week, we will do a presentation about your project. Each group will have maximum 15 minutes. I will post the rubric as soon as I finalized it on on Sakai. Okay. So next week would be our week 11. And then week 12, we are going to do review for final exam. Final exam is on April 26th. It is on the at your home. It is using virtual lab. It is actually similar to what we did in midterm test. So you go to Sakai, the questions are there. Specific information about final exam will be posted once it is finalized. Okay, so any questions about agenda, anything? So I'll try to open the chart so that I will also see your chart. Okay. Any questions? All right. So we do lesson 40 first. Both lesson 40 and lesson 41 is about parametric test. So what is parametric test? It has requirements about the distribution of the populations. Actually, the test we have done so far is parametric test. The non-parametric test, so lesson 40 and lesson 41 are non-parametric tests. Non-parametric tests do not have requirement from that sample comes from population with normal distributions. Remember, normally we need that requirement. If we need that requirement, usually we call it a parametric test. Okay, so for non-parametric test, we lose requirement. We do not require the population have normal distribution. Okay. There are some advantages and disadvantages about non-parametric tests. The advantages include it is a less rigid requirement. Okay, because it has a fewer requirements, less rigid requirement, it has wide range of applications. Okay. The second advantage, non-parametric data test can apply to more data types. Okay, for example, can apply to categorical data, can apply to the ranked data. Okay, So those are the advantages. The disadvantages of non-parametric test is that non-parametric tests tend to waste information because exact numerical data are reduced to qualitative form. So non-parametric tests, we usually dealing with the qualitative form. For example, the frequency count. Okay. So how many students come to campus by bus? How many students come to campus on foot? How many students come to campus driving your car? Okay, those are the frequency count. Okay. The other disadvantages is that it is not as efficient as a parametric test. Okay. Because of this reason, non-parametric test usually needs stronger evidence. For example, maybe larger sample size. Any questions so far? So now we'll go to lesson 40. One sample chi-square test, also called goodness of fit. Okay. First, I will introduce some notation. Capital O represents observed frequency. Okay. For example, I observed 20 students come to campus on foot. 35 students come to campus by bus. And 15 students come to campus by car. So those are my observation frequency count. Okay. The E represents expected frequency. Okay. Expected frequency, there are two formulas to calculate expected frequency. One, you use the sample size n minus the number of category. Okay, for example, in this example, what is the sample size n? You add all of them together, you get sample size. How many different categories do I have? I have 3 categories. Category 1 by foot, category 2 by bus, category 3 by car. So K equal to 3. Okay. So the expected value, I would expect 70 over 3, whatever that number is. This is the expected value. Okay. This is one way to calculate. Assume equal opportunities, equal chance. The other formula for calculate expected number is to use sample size times probability. Okay. So for example, I know based on the past study, I know percentage of people come to the campus is 32%, just for example, okay? And the percentage of people come to the campus by bus, it is 50%. And then the percentage of people come to campus by car, just for example, this is from the past study, okay? It is 25%, maybe, let me see, maybe 18%. So if you have those percentage, you can also calculate the expected value. Okay, so use the sample size 70 times 32%, you get expected value for by foot. And then 70 times 50%, you get expected value by bus. Lastly, you use 70 times 18%, you get expected value for by car. Okay, so that are the notations. The requirements for goodness of fit test is that data must be randomly selected, and data is frequency count, and expected frequency at least 5. As you can see from these requirements, there is no mention about normality. It didn't say population must be normally distributed. Okay, so this is a non-parametric test. Non-parametric test. Any questions? Any questions? Okay. All right. So let's move on to the next. To test the goodness of fit, we need to set up non-hypothesis H0. So H0 said the frequency counts agree with the claimed distribution. And alternative hypothesis said the frequency count do not agree with the claimed distribution. Okay. To do the test, we need to calculate test statistic. So the test statistic, we use chi-square. You use observed value O minus expected value squared. Then divide the expected value, add them all. Sigma means add them all. And this is the chi-square test. The distribution of chi-square skewed to the right. And the goodness of fit test, always right-tailed test. Always right-tailed test. So this one actually explained because there is a discrepancy between the observed value and the expected value. This is the discrepancy between O and E. So explain the test statistic. Okay. Now let's take a look at an example. Okay. Each person we have the body weight. Okay. In this study, we surveyed 2,784 males. And we asked them to report their weight. Okay. For example, I am weighing 143 pounds. So I am reporting this number. This is my personal data, 143 pounds. The last digit is 3, so I belong to here. So how many people report their weight last digit use 3, 111. So maybe people report their weight is 133, 123, 103, etc., etc. As long as your last digit is 3, you are part of 111 people. Okay, so this just to explain how this table comes from. And maybe some people will report their weight is 120 pounds. If you report 120, the last digit is 0. So last digit. How many people report their weight last digit is 0? 1,175. Okay, so this explains how this table works. What is the question here? What is the research question here? The research question asks you to test the claim that the sample from a population, the last digit do not occur with the same frequency. That is the test we are going to do. Okay, so the sample population, the last digit do not occur with the same frequency. This is our claim. Okay, and how do we carry out this question. First, we need to do the requirement check. There are 3 requirements for one sample, a chi-square test. Requirement 1, data are randomly selected. Requirement 2, data are frequency count. So all these numbers are frequency count. Number 3, requirement, the expected value is greater than 5. Okay, so what is our expected value in this situation? Remember, total we have 10 categories, from 0 to 9, 10 group, 10 different group, 10 categories. And if you add all the people together, total sample size 2784. So based on number of category K, based on sample size, we can figure out expected frequency E. E equal to sample size over K. So 278.4. This number greater than 5. So requirements are met. So now we are going to do the hypothesis test. Remember, we have 10 groups. Start with group 0, group 1, until group 9. We are saying the proportion of those groups are the same. Alternative hypothesis said at least one of them is different from others. That is our step 1. And then once we identify hypothesis and null hypothesis, how we are going to use SPSS to do the test. Okay. So in SPSS, I posted the data file on Sakai. If you go to resources, you can have this data file. Okay. I give you a few moments so that you can get the data. Go to Sakai. If you go to resources, you see this data. This is not it. If you click, do I have that data? Yeah, if you click mass 1p, if you click 1p98.sav, this is a SPSS file. Download to your computer. If you are in the computer lab right now, you can download to your local computer and you can directly open it because computer lab has SPSS. If you are online right now, after you download this file, you need to upload this file to OneDrive so that you can use Windows Virtual Desktop to conduct SPSS. Okay. I pause for a moment to see if you have any questions to get the data. Where is this data? Alternatively, you can manually quickly type in those numbers in SPSS. It is not a large amount of number. Okay. So I give you just a few moments. Make sure to have your data ready if you want to follow my steps along. At the same time, I'm checking the questions in chat area. All right, so In order to use SPSS, the very first step, you need to wait case. You need to wait case to conduct one sample chi-square test. So I'm going to open my SPSS. Try to also monitor your chart in case you have questions. Okay, so in this data, we have the last digit here, frequency. So I'm going to ignore other data. This is for another example, logistic, for another example. Maybe I will delete those. Those are just focus on this data here. So to conduct chi-square test, you need to weight cases first. Okay. So how? You go to data, weight cases. After that, you select weight cases by, and then you move the frequency into frequency table. You have to do this step before you can do the test. After that, you click OK button. Okay. So you wait the case. So after that, you do analyze non-parametric test, legacy dialogues, and then chi-square. So after you weight cases, you do this. Any questions? And then test variable is the last digit. Move last digit into test variable. And then under the options, that's fine. So just click continue. Exact test, continue. So you do not need to do anything. Just click OK button. And you get this result. Okay. So this result gives you the observed frequency. And the computer also calculated expected frequency. Remember, we did this calculation by hand. You use 2,784 divided by 10. Why 10? You have 10 categories, k equal to 10. You get expected value. And the residue is just the difference between observed 1,175 minus predicted or expected 278.4. You get residue. Okay. So I'm going to go back to my OneNote to make some notes. This is our output. I also posted on the OneNote. So this is the procedure, okay? And this is the output. You get expected value. So residue, it is just observed minus expected. In this case, minus 278. Okay. And the chi-square test statistic, you get 4,490. Okay, and how did you get this number? The computer used square, chi-square equal to observed minus predicted square it over expected, add them all. Okay, so let's do a few items. Can somebody try the first item? What do I write down? So based on the output, how can you write down? So sigma means add all. Let's write down the first number. So the first number is O minus E, square it. So this is O minus E, 899, square it, divide by E. E is 200, see this is E, 278. Okay, this is the first item. Sigma means add. Next item, so next item is negative 234.4, square it, divided by expected value. Keep on going. The last item is here, negative 213, square it, our expected value. And this result would give you 4,490.174. And this is our test statistic. Okay. And here you have degree of freedom 9. By definition, for one sample chi-square test, degree of freedom equal to number of category minus 1. We have 10 category, so that's why you get degree of freedom 9. And over here, we have sig value, that is the p-value. P-value is smaller than alpha. When p-value is smaller than alpha, you always reject H0. P-value smaller alpha, reject H0. So what is my H0? H0 said, you reject H0 in favor of H1. The final conclusion is at least one of the probabilities is different from the others. Okay, so this is a conclusion. And when you report this result, this is your interpretation, okay, or final result. I'll pause for a moment. Any questions? All right. So this is this one. That is a lesson 40 chi-square test for one sample, or goodness of faith test. Okay. Next, let's move to lesson 41, contingency table. Contingency table. What is a contingency table? It is just a table have a couple of rows, a couple of columns. Okay. All the number are frequency count. And you have row variable. You have column variable. Okay. So this is the contingency table. We use the same notation as we did in one sample chi-square test. O represent observed frequency. E expected frequency. We use R represent number of rows. C number of columns. 3 requirements. First requirement, the sample data are randomly selected. Second requirement, it is in two-way table, means you have many rows, many columns. For every cell in contingency table, expected frequency at least 5. Okay, so those are the requirements. Let's set up the test. The null hypothesis HO said the row and column variables are independent. They are not related to each other. Alternative hypothesis said the row and the column are dependent. They relate to each other. The formula for chi-square test is the same. We use observed minus predicted, square it, then divide expected, add them all. Okay. Let me check if we have some questions. This was already answered. My internet was missed-start. The computer bit for the project. Creating the course outline. The rubric will be posted soon. Eric, thank you for your question. All right. So let's return back to chi-square test for contingency table. And when you calculate expected value, you use this formula: row total times column total divide grand total. Okay. So for example, in this example, it is the data relating to autism and the measles vaccine. So the row totals, you have row total. So total autism, total we have 89. Not autism, total we have 1,789. So this is the row variable. And then we have a column variable, unvaccinated or vaccinated. How many people unvaccinated? 387. How many people vaccinated? 1,491. So the expected value, row total times column total. So let's say, what is the expected value for 25? So first of all, what is the meaning of 25? 25 means we have 25 people autism. They have autism, but they do not vaccinated. Okay, so what is the expected value for this 25? You use the row total for 25, that is 89, times the column total for the column, this is the column total, 387, and divided by grand total. This is the grand total, all the sample. And this number is the expected value for 25. Okay, any questions? Any questions? So now let's do expected value for maybe 64. What is the expected value for 64? Anyone want to volunteer? What is the expected value for 64? So what is the row total for 64? 89. What is the column total for 64? 1491 divided by grand total, 1878. So that is the expected value for 64. You keep on going. Okay. All right. So the result is 70 is the expected value, and you can calculate the expected value for other cells. Okay. So now we are going to solve a question. Is there a link between measles vaccine and autism? Okay. So we are going to use alpha 0.05 to test. So first of all, check the requirements. So samples are randomly selected. The results are all frequency count. The expected value greater than 5. All requirements are met. And then we set up null hypothesis. Null hypothesis said autism is independent of the vaccine. H1 said autism and the vaccine are dependent. Okay. That is step 1. Step 2, we calculate test statistic is 3.198. And then we calculate the p-value. You can use the Excel, just type in this formula, equal 1 minus chi-square dot dist, plug in test statistic, and then degree of freedom, and then it is true. So what is degree of freedom? Number of row minus 1 times number of column minus 1. In our example, we have 2 rows, we have 2 columns. So the degree of freedom is 1. Okay, so you can get the p-value. Obviously, this p-value is greater than alpha. When p-value greater than alpha, do not reject H0 or fail to reject H0. P-value greater than alpha. So this is the p-value approach. When you use the critical value method, you need to get the critical value. Critical value use Excel equal chi-square dot inv dot rt. Plug in alpha, plug in degree of freedom. You get a critical value 3.841. Okay, so critical value 3.841. Critical value decide rejection region. So this is the rejection region. And what is my test statistic here? This is the test start statistic. It is 3.198. Test statistic is not in the rejection region, so do not reject H0. The same conclusion as we get from p-value method. fail to reject H0. Okay, so what does mean fail to reject H0? So this is fail to reject. We are in favor of H0. The autism is independent of vaccine. We fail to reject H0. Any questions? All right. So that is the theoretical part. We did calculation by hand using Excel. How do we use SPSS? How do we use the SPSS? Okay. So we have to use this data. Not sure I posted. I give you a few moments. It is just very easy. Oh, first of all, we need to translate the data format into SPSS. So where is my original data? So this is original data. Okay, so original data. We just have 25, 64, 262, 1,427. Those four numbers are original data. All the totals are calculated. Okay, so based just on original data, 25, 64, 362, 1,427. How do you set up the data in SPSS? You do this. Remember, in this case, it is we have row variable and column variable. Okay, so row variable you can call it autism. This is a variable. Column variable you can call vaccine, VAC. Okay, and then you have number, NUM. You need to define 3 variables in SPSS. Okay, so now let's look at the autism. Autism has 2 values. You have autism, that is 1. Okay, so let's explain this 25. What does this 25 means? 25 means this person has autism, not vaccinated. So for autism, by the way, you are asked to do one question from textbook, exercise question, exactly the same as the question I am doing now. So pay attention to this question. Apply the same technique to exercise in lesson 41. Lesson 41 is in-class participation. Okay, so what you need to do in order to use SPSS, define 3 variables. The first variable, autism, the value is either 1 or 0. If you have autism, it is 1. If you do not have autism, 0. And then we have variable vaccine. The value is 0 and 1. If not vaccinated, it is 0. If you are vaccinated, it is 1. Okay, and then we have number. Number is just the frequency count. Okay, so now let's fill out this table. So what is 25? It is said this person has autism, unvaccinated. So autism should be 1, unvaccinated is 0. And how many people? 25. Now let's do next number, 64. 64 represents 64 people has autism and they are vaccinated. So they are autism and they are vaccinated. 1. How many people? 64. Okay, so keep on going. Next number 262. Those are no autism, unvaccinated. So no autism is 0. Unvaccinated is 0. How many? 262 or 362. Okay. And then last number 1427, no autism, vaccinated. Okay. No autism, vaccinated. Those are 1427. Okay. So this is the data structure in SPSS. You need to create this data. Create 3 variables, then type in the numbers. Okay. Because it is just for you type, I'll give you 1 or 2 minutes to enter those data in SPSS. Okay, so start with a new, start from the scratch. Just adjust my window so that I can see original data. Okay, create 3 variables. Or you can type in number, then create variable later. So this one, you type in 1, and then 0, 25, okay. Next one is 1, 1, 64, and then 0, 0, 362. Make sure you know how to do this, because in class exercise, you need to do this by yourself. So 0, 1, 1427. Type in the number now, you fix the variable name. You go to variable view. The first variable name, it is autism. First variable, vaccine. You just use short form, VAC. Last number is number, maybe just use NUM. And the number, they all have frequency count, so no decimal places for all of them. Okay. And also, yeah, so then go back to data. So you have this data here. Okay. I pause for a moment to see if you have any questions.
Excuse me, Professor.
Yes, Rhoda.
Do you still have to define in the variable view that 0 is for no autism and then 1 is for?
Thank you, Rhoda, for a great question. You could define the variable, or you couldn't. Both are okay. So if you want to define autism, so go to values, and then click the plus sign. 1 represent autism. Plus sign again. 0 represent non-autism. Okay, and then click OK button. So same thing for vaccine. Click plus sign. 1 represent vaccinated. Vaccinated. Then click plus sign. 0 represent unvaccinated. And click OK. You could do that, or you don't do it, but you know 1, 0 represent what. Okay. Thank you, Rhoda. Great question. So go back to this data. Okay, what do we do first before we do the test? Anyone remind us? Anyone? We enter the data, so what? Before we do test, what do we do? Jack? Sorry, put you on the spot. What do we do before we do the test? Okay, Ali. Sure. Rhoda. Okay, weight cases. When you do chi-square test, usually your weight cases. Okay, so go data, weight cases. And then quick weight cases by select number, put into the frequency variable. Weight cases. And then click OK button. After that, when you do contingency table, you do analyze descriptive statistics. And then cross tab. So raw variable is autism. Column variable is vaccine. Okay. And then quick statistics. We want chi-square test. Depending on what you want, we may just want chi-square test. Okay. And quick continue to make things simple. And then quick cells. We need expected value, so check out expected value. And also make sure observed value is also checked. And then click continue. That's it. And then click OK button. Okay. And you get this. Did I miss something? Yes, we have everything we want here. Okay, so I'm going to copy this to make a note. So I'm going to paste it here. So this is the total. We have this amount sample size. Okay. Expected frequencies are here. Expected frequency. Observed frequency are here. Those are original observed value. Okay. And we have a chi-square test. The same as we did by calculation. And we have p-value here. Okay. So this is how you get the result from SPSS. Get expected value, get test statistics, and get p-value. Any questions? All right. That concludes our lecture for lesson 40 and lesson 41, chi-square test. Remember, usually when you do chi-square test, usually, not always, you need to weight cases. And depending on you do one sample or you do a contingency table. When you do one sample, you just use after weight cases, you go to analyze non-parametric test, legacy dialog, chi-square. When you use one sample chi-square test, okay, And when you use a contingency table, you need to go analyze descriptive and then cross tab when you use contingency table. Okay. So any questions? All right. So shall we take a break? After break, I will give a lecture about logistics regression. Logistics regression is not on our textbook, but it is on the course outline, means it will be on final exam. Okay. All right, guys, I'm going to stop recording, take a break, come back at 10 after 2. Okay. So back at 10 after 2. Make sure you get some fresh air, get some water, stretch. Okay. I'm going to stop recording.